welcome back to the Comptia Network Plus course. Now, do we really need an IP address on a switch? The answer is absolutely not. Switches have all ports enabled and ready to rock. Take a switch out of the box, plug it in, and the switch starts learning MAC addresses in the CAM. But since switches are providing layer 2 services, why do we need an IP address? Because you still need an IP address for in-band management, which is used with your virtual terminals. That's why Telnet, SSH, Simple Network Management Protocol and so on all require IP addresses to communicate with the switch in-band through the network. And remember, since all ports are enabled by default, you need to shut down unused ports or assign them to an unused VLAN. Configuring a switch out of band means you're not going through the network to configure devices. You're actually using a port such as a console port to configure the switch instead. Most of the time you'll use the console port upon starting up the switch. After that, all the management will be complete in band. So now you know that the switch needs a management IP address for an in-band management purposes. But exactly where do you want to place it? Conveniently, there's something predictably called the management VLAN interface, and that's clearly your target. It's a routed interface found on every switch, and it's referred to as an interface VLAN 1. Good to know that this management interface can be changed, and all manufacturers recommend changing it to a different management interface for security purposes. Yes, you can buy switches that are unmanaged, but you may never want to do that for an enterprise network. The only environment in which doing that would make sense is in a home network, but that's about it. Anything you get for an office or large network absolutely must be a managed switch. With all that in mind, let's go down to configuring a switch now. We'll begin our configuration by connecting into the switch via the console and setting the administrative function. At this point, we'll assign an IP address to the switch, but as I said, doing that isn't really necessary to make our own network function. The only reason we're going to do that is so we can administer it remotely in band via a protocol like Telnet. Let's use a simple IP scheme like 192.168.10.16/28. And by the way, this mask should be familiar to you. Let's check out the following output. Switch enable, switch config t, switch config hash, hostname s1. S1 config hash enable secret Todd. S1 config int f0/15 S1 config if description first connection to S3 S1 config if hash int f0/16 S1 config if hash description the second connection to S3 S1 config if a hash speed 1000 S1 config hash duplex full S1 config if hash line console 0 S1 config line hash password console S1 config line hash login S1 config line hash line vty015 sconfig line hash password telnet sconfig line hash login S1 config line hash int VLAN 1 S1 config hash IP address 192.168.10.17 and subnet mask 255.255.255.240 S1 config if hash no shut S1 config if hash exit S1 hash IP default gateway 192.168.10.30, S1 hash banner MOTD hash, this is my S1 switch, S1 config hash exit, S1 hash copy run start, destination file name startup config, question mark enter, billing OK, S1 hash. In this output, the first thing to notice is that there aren't any IP addresses configured on the switch's physical interface, since all ports on a switch are enabled by default. There's not really a whole lot to configure, but look again, I configured the speed and the duplex of the switch to gigabit, full on port 16. Most of the time you would just leave these auto detect, and I actually recommend doing that. My next step is to set the console password for out of band management and then the VTY telnet password for in band management. The next task is to set the default gateway of the switch and banner so you don't get confused. I want to clarify that the default gateway is used to send management in band traffic to a remote network so you can manage the switch remotely. Understand this is not the default gateway of the host's default gateway would be the router interface assigned to each VLAN. The IP address is configured under a logical interface called a management domain or VLAN. You can use VLAN 1 to manage a switched network, just as we're doing here, or you can be smart and opt to use a different VLAN for management. The preceding configuration demonstrates how to configure the switch for local management, meaning that the passwords to log into the switch are right there in the switch's configuration. You can also configure switches and routers to store their usernames and passwords remotely for ease of configuration using AAA server. Doing this allows you to change the passwords at one device without having to telnet into each device separately to change passwords. To get this done, use the following command: S1 config hash AAA authentication login default. This tells the switch to use AAA when telnet or SSH is used for in-band management. This next command tells the switch to use the AAA server if someone is trying to access the console of the switch. S1 config hash AAA authentication login console. So remember, no IP address on physical switch interfaces, no routing protocols there either, and so on. We're performing layer 2 switching at this point, not routing. Switch port protection. There are many features that are available to mitigate switch attacks. In this section we'll examine some of these protections. Port security. Clearly it's a bad idea to have your switches available to anyone to just plug in and play around with your security. It's a big deal, even more of a concern regarding wireless security. So why wouldn't we demand switch security as much, if not more? But just how do we actually prevent someone from simply plugging a host into one of our switch ports, or worse, adding a hub, a switch or access point into an Ethernet jack in the office? By default, MAC addresses dynamically appear in your MAC forward filter databases, but the good news is that you can stop bad guys in their tracks by using port security. Figure 1120 pictures two hosts connected to a single switch port FA0/3 via either a hub or access point. Port FA0 switch/3 is configured to observe and allow only certain MAC addresses to associate with the specific port. So in this example, host A is denied access, but host B is allowed to associate with the port. By using port security, you can limit the number of MAC addresses that can be assigned dynamically to a port set static MAC address. And here's my favourite set penalties for users who abuse your policy personally. I like to have the port shut down when the security policy is violated, making abusers bring me a memo from their boss explaining why they violated the security policy. Brings with it a certain poetic justice, which is nice. And I'll also require something like before I'll enable their port again. Things like this really seem to help people remember to behave. DHCP spoofing. A rogue DHCP server, one not under your control, that is giving out incompatible IP addresses, can be an annoyance that causes users to be unable to connect to network resources, or it may play part in several types of attacks. In either case, DHCP snooping is a switch feature that can help prevent your devices from communicating with illegitimate DHCP servers. When enabled, DHCP snooping allows responses to client requests from only DHCP servers located on a trusted switch ports which you define. When any DHCP servers are configured to be trusted, rogue DHCP servers will be unable to respond to client requests. This protection doesn't stop there, however. The switch will also over time develop an IP address to MAC address table called a binding table, derived from snooping on DHCP traffic to and from the legitimate DHCP server. The bindings table will alert the switch to any packets that have mappings that do not match the table. These frames will be dropped. The bindings table is also used with ARP Inspection, which makes the configuration of DHCP snooping a prerequisite of ARP Inspection. ARP Inspection. Many man-in-the-middle attacks are made possible by the attacker polluting the ARP cache of the two victims, such as their cache maps each other's IP addresses to the MAC address of the attacker, thus allowing the attacker to receive all traffic in the conversion. Dynamic ARP Inspection (DAI) is a feature that, when configured, uses the DHCP snooping database of IP address to MAC address mappings to verify the MAC addresses mappings of each frame going through the switch. In this way, any frames with incorrect or altered mappings are dropped by the switch, thus breaking any attacks dependent on these bogus mappings. Because it uses the DHCP snooping database, and the configuration of DHCP snooping is a prerequisite to enabling DAI. Floodguard. Switches can undergo an attack where some malicious individuals flood the switch with unknown MAC addresses. Since switches record all MAC addresses of received frames, the switch will continue to update its MAC table with these MAC addresses until it pushes all legitimate MAC addresses out of the limited space provided for the MAC table in memory. Once this occurs, all traffic received by the switch will be unknown to the switch, and it will flood this traffic out all ports, basically turning the switch into a hub. Now the attacker can connect a sniffer to his port and receive all traffic rather than only the traffic destined for that port, as would normally be the case. This attack is shown in figure 11.2.1. Floodguards in this feature can be implemented to prevent this attack. It uses two mechanisms to accomplish this: unknown unicast flood blocking and unknown unicast flood rate limiting. The UUFB feature blocks unknown unicast and multicast traffic flooding at a specific port, only permitting egress traffic with MAC addresses that are known to exist on the port. The UUFRL feature applies a rate limit globally to unknown unicast traffic on all VLANs. When these two features are combined, flooding attacks can be prevented in switches that supports the feature. BPDU Guard. When a switch that is unknown to you and not under your control is connected to one of your switches, it can play havoc with your spanning tree protocol topology and may even allow the rogue switch to become the root bridge. As you know, when a switch starts receiving STP BPDUs from a new switch, the information in the BPDU, specifically the switch priority, is used to determine if the switch might be a new root bridge causing a new election, or if the STP topology should be changed. To prevent this from occurring, a feature called BPDU Guard can be implemented. This feature should be enabled on all switch ports that do not connect to known switches. Since most connections between switches and from the switch to a router are trunk ports, then it's generally enabled on all access ports or ports that connect to end devices. The effect of enabling this feature is simple but effective. The ports on which it is enabled will be shut down when a BPDU is received. While re-enabling the port can be done manually, you can also configure the port to wait a period and then re-enable itself automatically as well. Root Guard. Another feature that can be used to maintain the desired STP topology is called Root Guard. This feature is like BPDU Guard, Guard in that it also prevents a new switch from altering the topology. It is also applied to all interfaces on the current root bridge and prevent these ports from becoming root ports. Despite the name, root ports only present on non-root switches and represent the best path of attack to the root bridge. This feature prevents this by disabling a port if a BPDU is received that because of its superior priority number. This would cause a new root bridge election. It differs from BPDU Guard in that BPDU Guard disables a port where it is configured where many BPDU is received. This will be undesirable behavior on the route bridge as it needs to receive those BPDUs to maintain the topology. So in summary, it helps to maintain the current root bridge's role as the root bridge. So I'm going to leave it here today for this video. If you like listening, please consider sharing and subscribing. Thank you.